Very excited to be here, but I have the distinct pleasure of going second day, which means everything I wanted to say today has already been covered yesterday. So I was talking this over the dinner with some of you, what I needed to focus on today. So I went back to the hotel and redid some of my slides, so hopefully this is not a repeat. If it's a repeat, consider that this topic is very important, so it's worth repeating. If not, be patient. The point is to learn together. So my focus today, so I changed even the title of the slide. So I'm going to talk mostly about data for AI. All right, let me start with an experience that I went through about 5-6 years ago when I was working with a student, an atmospheric science student. He was trying to study wildfires, right? And he was specifically wanted to focus on environmental justice issues that was created by wildfires. This occurs, as you know, in Western US. It's a major disaster every year, right? The reason he wanted to study was there are multiple factors that contributes to fire and the effects of fire, right? It can create pollution, it can create air quality hazards, it can have health consequences. So to study this, NASA has this fantastic tool, visualization tool called Worldview. Someone of early career would go here to find the data, right? The first thing they would do is go through these images, right? We have a very nice history of supporting this large, high-resolution imagery through this interface. And anybody can go there and look through news article and go to certain day, find these images, right? So this is the image of Kincaid Fire in California. So next thing that person would do, or my student did, was to look at whether actually the smoke was caused by fire. So he would turn on this layer called thermal layer, which will tell you whether the smoke is caused by fire. Now, since he geolocated, and with time and space, he can go to a search interface. This is a NASA search portal for searching for data. He would type in something like fire. Now he already knows the date and time and location, and then he will get all the list of these data files, right? The idea would be to download those files and do some analysis with it, right? See the process of doing the science that is time-consuming here, right? These are pre-steps to do actual data analysis. So in the meantime, 5 years ago, one of my colleagues was also looking into outlining the smoke plume on NOAA's geostationary images. He was trying to study a different aspect of smoke. He was just trying to study smoke, how it evolves over time. So I was thinking, wouldn't it be nice if we can use his data to train a machine learning model so that my student doesn't have to go through this cumbersome process of getting into the data and doing data analysis. So, see this? Yeah. So this is the same fire, right? This is a very vanilla unit algorithm that we applied on this NASA MODIS data set over time, right? So this is very simple. Now you can do this across the 20 years of archive of MODIS imagery and create an event database, and you don't have to go through the process of doing data search and discovery, downloading, and doing analysis. But wouldn't it be even better if you can just ask a natural language query, right? How many active fires were there in Canada yesterday or something? You can change to Berlin, right? You can get, I don't think there's a fire in Berlin. But the idea is, this is getting really simple, right, to do. So what I'm trying to say here is that scientific process that leads into doing the science and scale analysis is getting changed fundamentally, right? Something that used to take my student a full day can be done in a few minutes. But I want to draw some distinction here between AI in general and AI in science. What my student was trying to do was AI for science, right? In AI in general, we are very eager to deploy, iterate, learn from that, and quit iterating in production, right? That's not how science works. Science, we care about robustness and accuracy, right? Because if you make mistakes, that could be costly, especially in health and disease diagnosis, and things like that. AI in general, we care a lot about publishing state-of-the-art benchmarks, right? We do that in science too, but science is fundamentally about understanding, right? We want to know when things fail and why it fails. AI in general, a lot of times, is detection and matching patterns. We want to do that too in science, but we also want to model this phenomena, right? Science is about phenomena, this partial differential equation. We want to model them, or a differential equation in general. Most of the time in AI in general, we want to automate things, right? But in science, we hesitate about automating the full life cycle. We only want to augment, make these repetitive tasks much more easier for scientists. And obviously, AI in general, we are looking at mostly one kind of data, image, sound, text, and so on. But scientific data is very heterogeneous and complex. Generally, when we do evaluation of AI outputs in general, there is an internal evaluation team, right? They do the evaluation. Before I get into details, I wanted to draw this distinction so that how AI for science is fundamentally different than AI in general. Okay, so when we talk about AI and earth science, there are two ways of looking at it, right? There are tools already out there, how we can use that to make science life cycle much more efficient, right? That's the first thing. But there are also advances in AI that can help us do better science, right? So today I'm going to talk about the first one only because I only have 45 minutes. This is because I work with many types of experts, scientists, engineers. I've worked in industry, business people, right? Scientists are by far the most creative people and most patient people I've worked with. They want to learn. They want to try new things, right? But they are also very patient. If it doesn't work, they want to help you with how to make it better. And that's why I want to focus on the first part today. So science is a process, right? It's usually we talk about the end product of the science when something is being discovered, but it is fundamentally a process where you have observations of data. You have a lot of different questions. Usually you look into literature to find those questions. Based on those questions, you formulate your hypothesis. You do a series of experiments. You do data analysis at scale. And you find conclusion, you publish or create a product, and so on. What I believe is AI can be infused in every phase of this life cycle. But I'm here to tell you that data is the key, right? Data is the key to doing the science, and data also goes through its life cycle, right? You have especially in NASA terminology, there's a mission which collects data, you generate these high-level products, you have to ingest an archive, you create this documentation so that people can search, you have discoverability tools, like I showed earlier, then you have a distribution mechanism, you can have a user support tool, and finally, there are products that are generated out of these experiments that also needs to go into the archive. And here also, AI can be infused in every step of this life cycle. So I'm going to focus on the science life cycle only today. So let's not worry about the observation questions, because observation technology, I think Philippe mentioned yesterday, there are already onboard AI capabilities, right, that are helping detect things in real time. There are also approaches, usually based on large language models, that are helping people identify these important questions in the literature that can be or should be solved. But in terms of hypothesis generation, we have so much data, we have so much publication. The hypothesis space is also growing large, right? So humans can consider a few of these hypotheses at a time, but to do it at scale or try to pick the right hypothesis, there are approaches. There are approaches like this, right? Actually, AI-driven approaches have found these gaps in researches that are helping people formulate new hypotheses. In terms of experiments, right, there are traditional ways of doing experiments, but there are also more efficient way of doing experiments nowadays, right? It can AI can help you choose what experiments to conduct, what are the optimized way of doing things, maybe less expensive experiments you can consider. And here's an example of doing a numerical simulation for weather forecasting. So this is a Clifford algebra-based neural network that is trying to forecast 7-day weather. This took, I think, about 4 GPUs, 5 hours to simulate. So traditionally, this will take about 4 or 5 days to simulate, right? So analysis is where AI has excelled already. We have seen a lot of progress in this area, right? Because there are too much data for human to process at a given time, and AI is this is where AI excels, right? Part of the reason is also that in science, we want to study these phenomena that doesn't occur very often, right? And it's like finding needle in a haystack, like somebody mentioned yesterday. It's the same thing here, right? AI is very good at finding needle in a haystack. So I just wanted to show you this one example. So this is search and analysis combined in one using AI, right? This is, Philip mentioned yesterday, the similarity search approach, where embeddings of these similar-looking features are created across time and space, and then you can index them over into a database, right? And then when somebody goes and looks for similar-looking images, like by clicking this image here, you can find everything that looks like that in the archive. Not only that, that's the search aspect, but if you can do that across time, you can do analysis like this, time series analysis, which can lead into climatological research, right? So one thing I think Alex mentioned yesterday, see, I'm going back to yesterday's talk because it's all mentioned yesterday. This cross-divisional, or maybe Hannah mentioned this, cross-divisional aspect of doing AI, right? Tools that developed for one particular domain can be readily, almost without any modification, can be used for another domain. So the same approach used for Earth science to archive, doing the similarity search across the archive. So the same approach was applied this is for Hubble dataset for astrophysics, right? So here, clusters of images are together that look like same galaxies. So this conclusion phase, a lot of people have already used AI, especially large language model, to synthesize their results and also write a publication. There are actually systems that help you full publication of your research, where AI agents can help you review the paper, and then the AI writing agents can help you address those reviews, right? I don't know how good those are, but things like that already exist. Okay, so a takeaway here is that AI has the potential to change every phase of this science lifecycle. It can speed up science discovery process, like my student did. Today, this is about data management, right? I showed you some search and discovery and analysis aspect of this data management for Earth observation data. And maybe one day, we can have AI also generate new hypotheses. Okay, now going back to NASA. So NASA has a bold vision, right? We want to reach the limit of where nobody has gone before. We want to reveal the unknowns, and we do that by doing science, right? We want to do science so that we can address the changing climate. We want to know whether we are alone in this universe. All of those are science-related questions that NASA tries to answer. And we do that by launching missions, right? This is a science fleet of 2023, I believe. So you see the volume of missions, right? From all the way from top left of astrophysics mission, bottom left is Earth science, top right is heliophysics mission, and the planetary missions on bottom right. So does anybody know what this is? Sorry? Yeah. So this is just one of those missions, right? So consider the volume of data we're collecting. All of this leads into data, right? These are some nice pictures. And it helps us address these strategic goals that NASA has. So coming to Earth science, this is what the NASA science fleet looks like. We have these missions that are ongoing, that are satellite missions, plus some of them are on International Space Station. There are also a lot of airborne missions and ground measurement activities that collect a lot of data. Some of these are partnership with the European space agencies and Japanese space exploration agencies. What this leads into is this, right? We have about 100 petabytes of data right now. That's 2024. And just look at the chart there. It tells you how the archive is growing exponentially. These are due to some upcoming missions that we have in plan. So this is a nice quote from National Research Council in 2002, which labeled NASA as a knowledge agency, right? That is interesting. The reason they're saying this is because we have all these missions that collect a lot of data to address a particular hypothesis, right? But it just so happens that these data gets used even way after the mission is decommissioned, right? By taxpayer-funded mandate, we have to keep the data openly available for people to use. And the challenge is how to manage that data and distill that into a meaningful knowledge. And that's our job at NASA. So now going back to some successes that NASA had in terms of science and artificial intelligence, some examples here. The top example is the data collected from SDO, Solar Dynamic Observatory, the heliophysics mission. If you look at the top row, the images have degraded over time, right? So the bottom row is what machine learning has been able to reconstruct the images successfully and well validated. Obviously, we have used computer vision techniques to land rovers in Mars. And there are also successful stories like actually finding new planets in planetary science using machine learning algorithms. Okay, this is a very unscientific study I did about 2 years ago, looking at a trend in AI publication in general science, right? This is looking at archive and AI. So obviously you see a nice trend after 2014-15, right? Because after the deep learning era. We wanted to compare that with NASA. So this is the NASA's publication trend. Almost a similar trend, although there is a little lag in it in terms of adoption, right? And we also looked into a little bit in detail how the people were using it. Most of the time, it is always supervised learning, right? You have a curated label data, you train it, you iterate over it. Once it reaches some threshold, you deploy it. And over deployment, you learn there are new things that you hadn't considered, you retrain it. In some cases, you need more data. And this is how most of these publications were doing this, using the AI for. And this is some NASA, in terms of supervised learning, what people have done over time. A lot of work on detecting these phenomena, atmospheric phenomena mostly. There are some optical imaging-based technique for detecting things like ships in the ocean, looking at these contrails in the sky, even societal benefit applications like marine debris detections, and there's some tool development to support these labeling aspects. There are also things that have been done at scale, right? This is a good example of doing supervised learning at scale. This is a group at Goddard that did this the application of supervised learning to actually count every single tree crown in Sahel region of Africa. When you think about desert, you really don't think about trees, but it just so happens that there are individually sparse trees, actually quite a few of them, more than 1 billion trees in this area. And the way they did it was they actually manually labeled almost 90,000 images of these tree crowns and trained it over a supercomputing center for the whole region. The outcome is interesting, right? Because now you can think of carbon sequestration from these trees and actually quantify the carbon storage in that area. Okay, so supervised learning, a lot of progress, a lot of uses in NASA, but there are also limitations. This is a workshop I ran in 2020, and some of you were there, I think. But two main things came out of that report. Training data bottleneck, right? We talked about this yesterday quite a bit. And the generalization of these models, individual models over space and time. Okay, so there have been recent progress that addresses some of these limitations, right? Mostly the self-supervised learning at scale. You've seen this a little bit about this yesterday. This is due to the advent of transformer architecture. Language model picked it up right after 2017. A year later, there are already a model, BERT model to be specific. And there has been model every year, 5, 6, 7 of them at a time. The vision side has lagged about 3 years, but as a lot of presenters yesterday talked about a lot of these vision models, right? So one of the results is the AI foundation model we talked about yesterday too. This addresses our two issues or two outcomes of that workshop that I talked about, right? It reduces the requirement of this training data set for downstream applications. And the effort to build a new custom model is much, much less, right? And the interesting thing here is that there's a corollary to foundation model to scientific approach, right? In engineering, you have a task, you build a system to do that task, right? In foundation model, it just so happens that you create it and let people explore what is the potential of it, right? And that's a very good corollary to what scientific process is. So the way we want to use these large pre-trained model is in two ways for data management, right? This workshop is about data management. The first on the left-hand side is the upstream, right? This is where all the meticulous things that goes into putting the data into archives so that people can use it, right? There's a mission, there's standard product development, ingest archive, documentation. That's where language models are very helpful, and we're trying to use that in data management and data stewardship. And sometimes large language models, as off-the-shelf general large language model, are not sufficient, right? You have to create a domain-specific model. We have tried this, general models. When you go to specific tasks, especially science tasks, it seems to fail. And obviously on the downstream task, we want to use foundation model, especially the science foundation model, to scale the analysis. Okay, so I think a lot of people have already heard about this model, the IBM NASA Foundation model on harmonized Landsat Sentinel. This was a partnership between IBM Research and NASA, and it has been adapted for many downstream tasks, also being used for teaching a remote sensing class, I heard recently. And this is done all following the open science principle, all the way from open meetings to open notes and source code. The culture is open. So we did this for harmonized Landsat Sentinel data set, and there's a reason to do that, right? This is our, by far, the most popular data set in the archive in NASA Earth Science. This is the second most popular because MODIS is still even though it's decommissioned, it's still the most popular data set. And it's been cited about 8,000 times already. It provides you nearly 2 to 4 day global coverage of the whole Earth. And it's been downloaded 2 petabytes of download already. And you can see the animation here, how the 2 sensors from ESA, the Sentinel-2, and from NASA, Landsat, those were, you can basically interchangeably use that using this approach. So the way we want to use this foundation model is provide as this central interface where people can come and do multiple different applications supported by one model, right? This is just a very prototype development to showcase the power of this foundation model that I just talked about. So there are two examples here, burn scar detection in Maui, right? And the flood detection or flood segmentation in Libya, the two more recent events, both fine-tuned for two different applications. All right, there are challenges, however, right? With my experience of doing supervised learning to foundation model, there are many, many challenges, and I'm going to highlight a few of them today. So this is very expensive, right? Especially foundation model development is very expensive. You have these four main things, and there could be more I could think of. You have to develop, you have to support, you have to have infrastructure, and if it's good and you ultimately, for me, AI research is fine. You have to put it in production for people to use it, right? So operational side of the things. And then there are too many of these executive orders and compliance mandates are coming up, right? So you have to follow those regulations too. So in terms of development, you need AI expertise to build foundation model, right? You need data science expertise and also engineering expertise. You still need to do labeling for your fine-tuning tasks. You need science data as is not really useful for AI as is, right? You have to do some pre-processing. And I talked about validation, right? You need science community to validate your science foundation model. Infrastructure-wise, you need computation, obviously, lots of GPUs and storage. Operation, you have to monitor over time. Things change, right? You have to adapt, and at some point, data is coming more frequently at bigger scale. You have to adapt. You have to scale it. So this is, I only have few numbers here. I don't even have numbers for compliance and pre-processing. This is some off-the-shelf number I calculated in terms of that Prithvi, the geospatial foundation model for 100 million parameter. This was a 6-month effort. And the technical expertise, the cost was $2.5 million. Data labeling, our estimate was about $5 per label, right? We need thousands of these. In terms of computation, the GPU cost was about $130K. And if you want to run that in operations, you would probably want to run it with some set of GPUs, right? For inferencing and in some cases, fine-tuning. That costs about $1,000 a day. Just imagine the cost here, right? That's the number one challenge. Number two is taking these research outcomes to production, right? Usually what happens is you do the science, then you publish a paper. It ends here, right? Then you have to deploy and interpret for people to use it. That is an iterative process, right? Things change over time. Let me give you one example. This is a 2015, I think. One of the first things I did, a deep learning exercise, was to take these years and years of satellite imagery, right, and use that to estimate the wind speed during a hurricane. This is a niche area, nice area, because we have collected this satellite imagery for storms for almost a century, right, and we have corresponding wind speed values for this imagery. So this is a good application for AI. So we did this, as you can see in the bottom chart, when the things are not organized in the storm, it doesn't do very well, but as it grows, you can see it does fairly well in terms of estimates versus the actual. So the reason I'm showing you this is we thought this was really great. We published 2 papers, right? We put it in production. Production meaning not for people to use it, but to test whether it works with the new data. And it failed miserably, okay? The thing was, there are a lot of data-related issues here, right? The images and its corollary, the estimates, a lot of them, we found a lot of mistakes. So this is where I'm getting into data-centric approaches. And And it also didn't work well with new hurricane seasons. As you know, the climate is changing. There are new patterns being formed. So that was quite a awakening for us to deploy these things in production. What are the things you need to consider? So there's a cost associated there too. I think this chart, this paper was shared yesterday by Alejandro yesterday. One of the things I have also realized is when you form an AI team, and nowadays everybody's AI expert, right? You have this democratized the tools and applications, the tools and libraries that are available for everybody to use, which is good. A lot of times you get hits, right? But the foundational mathematical knowledge of AI is critical to have within a team, especially when you do AI for science. There has been instances of misleading results because of not having that mathematical expertise within the team and deriving these scientific outputs. Obviously, ethical issues, I think a lot of you are already aware of this. This is some work that we funded to do ethical AI for science, and they published this paper. The idea was to bring community together, especially scientists and the social scientists together, to address some of these, right? Especially the model biases and data biases and transparency issues. Okay. There are some good things too with the pre-trained large language models, right? So we have talked about big data for a long time, right? What I want to show you is these large language models have shown the value of small data. So we know AI, especially foundation models, scale with compute, data, and parameters. This is a good paper. If you haven't read it, you should read it. So let's look at the evolution of GPT. It was trained on everything on the internet, right? That's why GPT-2 was developed. GPT-3, they added more data. ChatGPT was created over GPT-3 by using label data, especially the reinforcement learning with human feedback, right, RLHF. So once you have ChatGPT, you can use your own custom data to create your own GPT, right? This is done. People have done it, and it works. So what is the key here? The key is the data. Data is a differentiator, right? Model has remained the same. The architecture has remained the same. So let's look at the AI foundation model in science. You start with raw data. You do a lot of pre-processing, right? You cannot possibly use every single pixel that we collect to develop a science foundation model. You do some intelligent pre-processing, right? Samples, subsampling. Then you run your transformer architecture to develop foundation model. Once you have that, there are many ways to use that. One way to use it is zero-shot learning, meaning that you try to generate output from the foundation model, which hasn't been tasked explicitly for that particular task. Second way to use it, few-shot learning, basically showing some examples, right? This is prompt engineering in large language model, right? You show some examples and try to try to generalize that for your application. And third thing, which is a little bit more involved, is fine-tuning. So fine-tuning is basically taking the weights from the pre-trained weights and try to do transfer learning for your particular data. So this is a little bit more involved. But the outcome is that you have your custom model after all of these exercises, right? That you can deploy it, and you can create your own APIs and serve it, right? So why I'm showing this left side is a big data problem, right? We have lots of data. You need a large collaboration. It's hardly ever one person can develop a foundation model. Once you have that, it's individual researchers who can actually go and just use a small set of data to create your own custom model. And the example we have from HLS model is that in some cases, we were able to fine-tune a model to get to the same level of accuracy by using 87% less training data set. Do I have time? I was going to show you a couple of examples. This is, you probably didn't expect me to do coding during keynote, did you? This is going to be dangerous. Okay, I tried to run a notebook, so it actually ran already. So large language model, right? We can use to make our search and analysis process very efficient. So this is one example. I'm not going to run it again. I just ran it right before the talk. But you can see, you can have a conversation like, provide me daily time series bar plot of nighttime fires during California, right? So it generates a nice chart here. So not only is doing searching, it's actually doing analysis for you. Are there fires in Berlin? Probably not. Oh. Sorry, how do you spell that? R-A-N? Oh, Brandon. Like that? Was there a fire recently? Every summer. So not January, then July? I'm not saying this will work.
While we're waiting, can I ask a question?
Oh, there were fires.
What makes you think that's right?
So this is coming from the archive that has already ingested the fires from the past. So this is coming from a science data. This is not, the question answering part is going through, the generalization is going through the OpenAI interface, but the actual information is in the science database in NASA. Yeah, I should have made that clear. It's not asking ChatGPT to do this. Sorry. Okay. Maybe one more example. Since it works, I'm getting greedy here. Okay, so we have a catalog system called CMR, Common Metadata Repository, which is basically a catalog for everything we have in earth science, right? And usually you interact with that using API, set of APIs. You see where I'm going with this, right? So wouldn't it be nice if you could talk to the API or just have a natural language query, right? So I'm not even framing this question in a right way. I'm not even saying what is the, right? I can just say data to monitor landslide caused by earthquakes in California in the last 5 years. So it gives me the start date and end date because it figured out. So the way this works is this, right? You have to create these, you have to let the system take a role. So this is what the AI agent is the new thing nowadays, right? You can say, hey, action you take is, these are the set of tools you have available. These are the results you need to do. Once you have the results, do something with the result, right? And basically what it does is it figures out today is this day. It goes far 5 years. Because I said 5 years, it knows how to geolocate California. So it constructs this query, runs the query, and it gives me the set of data set. But I can also ask some completely nonsense question. What is osmosis? You don't have anything related to that in science, in NASA catalog. So it says the query, what is osmosis, does not pertain to CMR API, right? So it's grounded by the truth. It's grounded by what we have in the catalog. And that's one of the things we want to prevent is hallucination. Yesterday we talked about hallucination, right? So we can do things like this to ground the scientific results and certain set of corpuses so that the outcome from the generative AI is meaningful. Okay, I think I just about ran out of time, so I'm not going to do any more demo. All right, so I want to go back to the supervised learning, right? This is what we started with. This is where we had a lot of success, supervised learning. So the way things are moving nowadays is with the small data. You can develop these prompts, right, and deploy the model, and just iterate over that, right? So this is the value of small data that we are seeing in NASA. Even though we have big data, I think this AI has allowed people to work with small data and deploy their model much faster and hopefully much cheaper. This is some considerations or thoughts that I had about data and pre-trained large language models. Foundation models are basically data representation. It's very data-centric, right? Model architecture has remained the same. Data requirement for custom model development, if you use pre-trained large models, is getting much smaller, which probably means lower cost. One thing that we have always followed is this open science principle for foundation model, right? Open data, obviously science quality data, transparent approach, building communities together. Also, one thing we're seeing is this governance aspect of data and foundation models. I think it's getting more and more complicated now with foundation models because a lot of these closed models, they do great things, but they're not transparent, so how do you govern that? So far I talked about the first thing, right? How, yeah. I don't know what happened. Yeah. Okay. So far I talked about what AI can do for science, but there are also AI advancements that I think can help us, right? So one thing is AI is algorithm and data, right? Lots of data in this case. Wouldn't it be nice if there are algorithms that can work with smaller data and get the same level of performance, right? Because in science, we're working with these phenomena that are very rare, that happens very infrequently, right? We're interested in those, and those, how can you, are there algorithms, are there advancements in that area? Data management is the key. What data to keep, what to throw away. Yesterday we talked about that, right? If AI can help with that, that's great. Cross-disciplinary tool, right? There are tools that work off the shelf from one domain to another. Then we need to investigate more on that. Optimization technique, especially in the foundation model, we ran into this. Yeah, it's good to have a lot of these infrastructure, GPUs, but keeping GPUs busy is a different art, right? And that's something advancement in AI can help us with. Obviously, ethical and explainable AI is a big key when you're working with scientists. You need to be able to explain to them. Holy grail is automated hypothesis generation, right? How can we let AI come up with their own hypothesis? And above all, can we have a cheaper options to do these large-scale foundation models? All right, my last slide. So from AI perspective with NASA and Earth Science, there's unlimited potentials. We've been working on this for a long time, but we want to do that in a collaborative way, right? Open science principles. It's not just open data, open models, it's a collaborative culture, right? And that's a good example we did with IBM Research, with like-minded organizations with common goal. Obviously, we want to build responsibly and safely and openly. We are looking at the whole life cycle approach for AI, infusing it into science research life cycle. NASA is known for doing rigorous evaluation with all the way from rocket, everything, right? We do follow the same principles when we develop AI and we put it into production. Very rigorous and careful evaluation. One of the things we're focusing more and more is this diverse input, not just for the ethical side of the things, but it's important to have a team that includes a diverse set of people. And ultimately what we want to do, I want to go back to that mission chart, right? We have lots of data, right? I just showed Earth Science data. We want to maximize the potential of data and through AI. That's all. Thank you.
Thank you very much. I think we have time for one question because we ran out of time. Anyone want to ask a question? Yes, one here.
Thank you. Thank you very much for your presentation. And as part of it, you mentioned that it's important to also deploy these models in the real world and try to get feedback and gain more knowledge from them. But then what's your recommendation for universities? So how are they Like I don't think they have the funding to deploy models or the incentives to do so.
So, yeah, I don't know how that works in Europe, but in US, there are operational organization, there are research organization, and there are usually something in between whose job is to take research products and work with the end users and mediate that, right, and advance that over time. It's there, so you work with that transition group, right, to see what the demands of the operations is, right? There could be, your model is probably some data, right? You need to put some sort of interface so that the end user can understand. So this team in between actually helps you mediate that transition. And funding-wise, yeah, that's. At NASA, and we do support that transition phase as part of the research. I'm not sure here how it works.